let's look at the behavior of light. As light goes into a different medium, the light will slow down or speed up just a little bit. Significant is that this difference depends upon the frequency. So some frequencies will slow down more than others. The result of this is that if white light enters a prism, the prism will spread out the light according to its frequencies, which is to say different frequencies will respond differently, and the result is that you can find out what the light basically is made out of. White light will give us a nice rainbow. This is a pretty familiar image. Light in a room like on the planet Earth with atmosphere and lots of light from the sun and other sources is a very random sort of thing. Photons are absolutely everywhere doing absolutely everything. And photons have different energy levels and probably bounce and reflect pretty much the same, but the energy levels make a difference to us as human beings able to see. A photon will strike an object, let's say right here, and it will reflect off that object into the lens, be focused, and end up right here. Arbitrarily, another photon will strike the same spot, arbitrarily, will strike the same spot, and will go to this spot and then be focused to the same spot. Down here, a photon will arbitrarily strike this spot, be focused onto this spot. No matter where it comes onto the lens, it will be focused onto this spot. And the enormous amount of photons in a given space moving in an arbitrary fashion, there's going to be a photon that's going to do exactly what we needed to do to put an image on our retina. A camera works the same way. Exactly. The camera is, of course, filled with air, which is clear. The material in our eyes is also clear. So the photons just go right through it. Images of outer space are sometimes very helpful for physical science. Let's go out into space, take a red flashlight, and shine the flashlight off into space. The red light travels out into space, and it doesn't turn into something else, and it doesn't tire out, and it doesn't slow down. The red light just goes and goes and goes, and that's it. It just goes and goes. It never turns into something else. It never changes into something else. It's spread out as it moves away. This is important in astronomy because light that left a star 200 million light years ago has been traveling for 200 million years. The light that we're seeing from the star is very dispersed because it's very, very, very spread out. But it's the same as the light that left the star many, many years ago. Everything has been described as either matter or energy. So everything is matter or energy. Well, the matter side of it is easy. Matter is things like pencils, maybe the paper I use for notes. I have a little snapper thing that's matter. Pens, boxes for me, the air, water. Everything is matter. The conservation of matter is sort of easy. Chemical reactions take place. There's no matter interchange. Everything is matter or energy. So that says that everything includes energy. To me, this sounds like a promotion for energy. Energy is promoted to energy is like a something. It's like a physical thing, which is consistent with conservation of energy. Energy is something that you can't create or destroy. Energy is a something. The red light leaves the flashlight. The red light is a something in the same way that matter is. Matter is something. This pencil is not going to do anything unless something is done to it. The red light leaves the flashlight, travels out into empty space, and nothing will happen to it ever, ever, ever until it interacts with something. Let's take a look at this again familiar graphic. This is a small piece of the electromagnetic spectrum. We see, literally in this case, we see red light and yellow light and green light and blue light. It's more important from the standpoint of physical science to look at these as energy levels. We have an energy level that we see as green. We have an energy level that we see as blue. So they're really energy levels in a more important way than they are colors. The energy levels are not, this is a very important concept in what I'm trying to put across here. The energy levels are not interchangeable. Green light is not red light. It's never going to be red light. Blue light will never be anything but blue light. And then the last point on this is that this is, of course, a small slice out of the much larger electromagnetic spectrum. The energy is related to the frequency, which is, and this is a visual image, the size of the wave is the frequency of the how far apart are the waves is the critical issue, not how big they are. It's not how big they are, it's how far apart they are is the issue. So the smaller the waves, the higher the energy. And from our visual perspective as human beings, the high energy side is the blue side and the low energy side is the red side. You go off the blue side and you get to ultraviolet, which are actually the ones that cause sunburn. You go off on the red side and you get to the infrared side, all of which have uses in chemistry. We are defining Solvinski's box as a label for things which can be known but never really understood on an intuitive level. Many of us have been working with electromagnetic radiation and energy levels and that kind of thing for a long time, and we're very comfortable with it. But the idea of light, not so much its behavior, but what is light, is something that we're never going to be able to really, it's not something that you're ever going to be able to understand on an intuitive level, like a falling rock. You can understand that. Or forces of like force equals mass times acceleration. You can put that on an intuitive level. You can't really put a lot of chemistry and physics on an intuitive level. And I think that for matters of academic honesty, I think let's kind of give it a separate label. And I think it'll make it easier to learn. It's not like Solvinski's box is terribly difficult, but it's an abstract leap for the person that's trying to learn it. The objective of this series is that we want to climb down into Solvinski's box, and we want to look around in there, and we want to demonstrate the rather interesting and cool relationship between electromagnetic radiation and molecular structure.